morning everybody, my name is Oral Djallal Eddine, a PhD student at University of Al-Hajj Bushaib, INT Motion. I'm going to speak about an interesting subject which titled the structural and the electronic property of Half-Heusler ARSB in the absence and the presence of a spin-orbit coupling. So the main outlines of this case study is introduction, Half-Heusler Alloys with the 18 valence electrons, computational methodology, result discussion, and finally we have a conclusion and perspective. So one of the principal challenges facing the world in energy at present is a drive research for alternative energy resources such as thermoelectric materials because the thermoelectric effects enable direct conversion from thermal to electrical energy. In the last decade, Heusler compounds have attracted significant research attention for their thermoelectric property, despite their chemical similarity. Different compounds within this class of material exhibit very different electrical and thermal transport properties. So, Heusler compounds are among the best known intermetallic compounds such as Ful and Half-Heusler. The composition of Heusler compounds are represented as shown in this figure by the chemical formula X2YZ and XYZ for Ful and Half-Heusler respectively, where X and Y atoms are transition or noble metals and Z is a main group element. So the two compounds crystallize in cubic structure with two different typical structure and the space group as shown in this slide. So we notice that Half-Heusler structure can be obtained if one if one of the two X lattice is vacant. So one of these compounds that we study here is XARSB, where X corresponds to titanium and zirconium atoms. It means we have two compounds that we study here, such as TAARSB and ZRARSB, which is classified within transparent conductor. Zirconium, antimony, titanium, iridium are part of 4th and 5th group in periodic table and will be alloyed into many important materials, such as thermoelectric materials, because of their interesting physical property. So this table here shows the crystalline structure of the two compounds such as TAARSB and ZRARSB, and it's clear that have a Half-Heusler structure where we can describe it by the interpenetration of a three-phase centered cubic sublattice occupied by the three atoms XYZ with the following Wyckoff position. So our aim in this present work, is studying exchange correlation and the spin-orbit coupling effects on our compound, such as structural property by calculating lattice parameter correspond to each approximation used here, as well as electronic property by calculation band structure and gap energy. So before going to the results obtained in this work, the following slide represents computational methodology of our study. The methodology used in this work is the ab initio study with a plane wave and the pseudo-potential method were performed by using quantum espresso package, which implemented density functional theory. So we used the three approximations of exchange correlation, such as GGA, GGA plus U, and meta-GGA functional with and without including of a spin-orbit coupling. So the most successful and widely used for GGA approximation called PBE, and on the other hand, the recently developed meta-GGA called scan functional. So for the pseudo-potential used here, we used two types. So the first one is an ultra-soft pseudo-potential. We use it for GGA approximation or for PBE. And the second one called a non-conservative pseudo-potential, and we used it for a scan functional. Moreover, and to optimize a structural parameter, we have the cutoff for kinetic energy was fixed to 50 Rydberg, as well as the zone-Breuer integration was fixed on 10 key-point mesh. So in this section we calculated the ground state property for the two compounds by the optimization of their cubic structure with a specific group of F43M for both compounds using Birch-Marnegan equation of state. So the following figures show the variation of the total energy as a function of volumes using the three approximations such as PBE and PBE plus U and the scan functional in the presence and the absence of a spin-orbit coupling. So independently of spin-orbit coupling, the result illustrated and there's a figure here show more stable structure in the case of a scan approximation, where the total energy is lower than obtained in the case of PBE and PBE plus U for both compounds, while the inclusion of SOC extends slightly total energy for TAARSB and ZRARSB with all approximation used. So the lowest energy of the relaxed structure is attained at equilibrium volume, which corresponds to the lattice parameter listed in this table. This obtained lattice parameter varies slightly between 6.123 angstrom and 6.194 angstrom for TAARSB when we go from exchange correlation approximation to other ones. So it means when we go from PPE to PPU to PPE plus U to scan functional. And this variation is similar for ZRARSB, where it varies between 6.306 angstrom and 6.379 angstrom. And we can explain this variation of optimized lattice parameter value for TERSB and ZRARSB by the difference derivatives in treatment of core electron for each approximation used in this section. And we notice that the lattice parameter of ZRARSB are about 0.18 angstrom, larger than those of the TAARSB compounds. This can be easily explained by considering the atomic radius of ZR atoms and TA atoms, where the radius of zirconium atoms equals 1.55 angstrom, and for titanium equals 1.4 angstrom. And we know that the lattice constant increases with the increase of atomic size. So for the results obtained with spin-orbit coupling, the lattice parameter values are almost similar to the results obtained in the absence of the spin-orbit coupling. Thus, the spin-orbit coupling show no important effect on obtaining the structural propriety. So we present in this section the best structure of the two compounds, such as TAARSB and ZRARSB, along the first Brillouin zone direction at zero temperature with and without including of a spin-orbit coupling. So for all approximation, the calculations show that XARSB compounds are an indirect semiconductor as a valence band maximum and the conduction band minimum are located at a difference Higgs symmetry point in the first Brillouin zone. And the results agree well with the previous books. So, and we notice that in the absence of SOC, the figures show an increase of the band gap when going from PPE to PPE plus U for the two compounds. So it's confirmed that Hubert potential corrects the effects of self-correlation yielding and underestimation of the band gap. However, when we comparing the calculation using scan functional in the absence of spin-orbit coupling, we observe that a good performance of scan functional for ZRARSB compound, while in the case of TAARSB compounds, it seems that PPE plus U plays a better role to describe the band gap than scan functional. So the inclusion of spin orbit coupling causes a splitting at the valence band for the two compounds, while the conduction band is not affected by spin orbit coupling. However, the highest and the lower occupied state are shifted upward and downward respectively. So from these figures we can see that the values of spin orbit coupling splitting for ZR-ARSB is greater than that of TA-ARSB for all functional used here. This can be explained by the strength of spin orbit coupling, which becomes very important for transition metals element, where the ZR atoms is heavier than TA atoms. So the following table shows the band gap value of the two compounds for all approximation in the presence and the absence of a spin orbit coupling. And it's clear that the using of PPE plus U and the scan factional gives a better description of the semiconducting behavior than for the two compounds, where the both approximation open the gap between valence and the conduction band, while the inclusion of SOC of spin orbit coupling, it means, decrease the band gap value for all approximation used in this section. So the following histogram here shows the spin orbit coupling effects on gap energy for a different approximation of exchange correlation. And it's clear that the spin orbit coupling effects is more important in the case of a scan functional, where the difference between a gap energy in the presence of SOC minus the gap energy in the absence of SOC equals 0.48 electron volt for TA-ARSB and 0.54 electron volt for ZR-ARSB that we study here in this work. So finally, our aim in this work is making a quantitative and a qualitative study of a spin orbit coupling effects on structural and electronic property of these compounds, which is classified as a transparent conductor using a different approximation of exchange correlation, where we found that the spin orbit coupling effect is almost neglected in the structural parameter or in the structural property, but on the other hand has an important role in the electronic property such as band structure and gap energy. So in the future we look forward to studying the contribution of atoms for each approximation used previously, so as to further understand the physical property of this compound. So that's what we have until now, and thank you for your attention.